Welcome to A-Level and AP Physics. In today's lesson, we will discuss a typical type of question on nuclear physics from March 2022, Paper 4, Variant 2. In this question, we will discuss how to complete the nuclear equation for alpha decay, how to calculate nuclear activity, and how to sketch graph of daughter nuclei against time. At the end of this lesson, we will also discuss how to calculate energy released in a nuclear decay. So in this video, we will discuss some very important point about nuclear physics. So listen carefully and try to improve your understanding of this topic. For question number 9, it is given to us plutonium-211 decays by alpha emission to form a stable isotope of lead. For part A, we need to complete the equation for this decay. It is given to us this is alpha decay. So first of all, we can write down atomic number and mass number for alpha particle. Now we have to complete this one. So this is 84 minus 2. So this one has to be 82. And this is 211 minus 4. So this one has to be 207. So that's all what we need to do. And this question has 2 marks. If you have done this right, you will get 1 mark. And if you have done this right, you will get the second mark. For part B1, it is given to us at time t is equal to 0. Sample only contains plutonium-211. For part B1, we need to use figure 9.1, means we have to use this figure, and we need to determine the decay constant lambda of plutonium-211. Give a unit with your answer, means we have to write down the unit for answer as well. Now this question is asking us to calculate decay constant. Decay constant simply is equal to ln 2, or simply you can say ln 2 divided by half-life, but ln 2, this is equal to 0.693 divided by half-life. So this is divided by half-life. Now simply we need half-life. If we have value of half-life, we can calculate decay constant. In order to find half-life, we need to use figure 9.1. So we can write on here, this is 0.693. We have to divide by half-life. Initially, we have 24 number of nuclei, 24 times 10 to 12 number of nuclei. So when these nuclei become half, means they become 12. That time taken, that is equal to half-life. So simply you can read this one from here. This is 0.52. So this is half-life, and half-life is in seconds. So simply we can write on here. So this is 0.52 seconds. So we will write on unit here as well, lambda. Now we have to simplify this. If we simplify this one, our final answer will be 1.3 per second, because this is in denominator. So this one is over answer. This is how you can calculate. Let me explain you a different method to answer same question. If you want to use a different formula, you can use this one. You can use n is equal to n naught e to the power of negative lambda t. And t is the time taken for n naught to become n. So this is value of t. For example, in this case, we have n naught that is equal to 24, and you want to use n is equal to 10. So you can take value of t from here. So in this case, this one will be the value of t, and you can use this value of t, and you can use this formula, and you can calculate value of lambda. But you also need to understand the derivation, means we can use this formula and we can derive this one as well. So this formula we can derive from this basic formula. So let's try to understand how we can derive formula. But if you're curious to use this formula, you can take any value of t, means the time value of t when n naught, initial number of nuclei, they become n. You can use that value of t instead of using half-life. You can find value of lambda, but this will be a little bit long method, and this one is smart way to answer this problem. If half-life is given, lambda is given, you can calculate half-life. If half-life is given, you can calculate lambda using this method, using this equation. Let's try to derive this one. Imagine that n naught, this decays to n naught by 2, means half number of nuclei decay. So then we can write down e to the power of lambda, and the time taken, that will be equal to 1 half-life. So in this case, we can cancel n naught with n naught. So we left with 1 by 2, and this is equal to e to the power of negative lambda times 1 half-life. Now, if we take natural log on both sides, ln of 1 by 2, and here we take ln of e to the power of negative lambda times 1 half-life. Ln 1 by 2, we can write down ln 1 by 2. This is equal to ln 2 to the power of negative 1. So we can say negative ln 2. So minus sign in front of ln 2. So we can simplify this. We can say this is negative minus sign here, ln 2. And this is equal to ln e. But ln e, you need to understand, ln e is equal to 1. So ln e is equal to 1. As ln e is equal to 1, so simply we left with minus lambda t times half-life. So this negative we can cancel with this negative. Now simply we can write down in this case lambda is equal to ln 2 divided by half-life. So this is how we can derive this formula. Ln e is equal to 1. So this is also important point. You need to understand ln e is equal to 1. Simply you can say ln and e, they cancel each other. For the second part, we need to use answer from B1 to calculate the activity at time t is equal to 0 of the sample of polonium 211. We need to calculate activity, and activity is equal to A times lambda n. We have to calculate activity at time t is equal to 0. So here we have time t equal to 0, and we have number of nuclei. So at t is equal to 0, we have number of nuclei, that is equal to 24 times 10 to 12. And value of lambda we have calculated in part B1. That was equal to 1.3 per second. Now simply we have to multiply these two. So we can plug in value of lambda times n. N is equal to 24 times 10 to 12. So if we simplify this, our final answer will be 3.1 times 10 to 13 per second, or simply we can write down BQ, means number of decays per second, BQ, background. That's all what we have to do for this question. If you got right answer, you will get 1 mark because this question has only 1. So this is our final answer, up to 2 SF, because least number of SF in raw data we have 2. So our answer also has 2 SF. So we can say 2 SF. For the next part on figure 9.1, we need to sketch a line to show the variation with time t of the number of lead nuclei in the sample. But for this question, it is given to us that polonium decays into stable isotope of lead. It simply means that total number of nuclei at any given time has to be equal to number of polonium nuclei plus number of PB, means lead. By keeping this fact in our mind, we can sketch the graph. So the graph will be just reflection of given curve. So let me show you how you can sketch the graph. This is how you can sketch the graph. Now if you look at this point, we have 12 nuclei of lead and we have 12 nuclei of polonium. And if you look at T is equal to 0, we have 0 nucleus of Pb and we have 24 nuclei of polonium. And this is true. You can also check at any point. This has to be true. So this is how you need to sketch the curve. So this is blue curve you have to sketch. So this is for number of nuclei of lead. So this curve you have to sketch. So you have to be careful with this point. You have to be careful with this point. Now if you look at this one now, at polonium, you can see this is one big square and three small square. And if you look at this one, we have one big square and we have small 3 square. So it simply means that it just reflection. So this curve curve is just reflection of E1 curve. For part C, it is given to us each decay releases an alpha particle with energy 6900 kilo electron volts. For part C1, we need to calculate in joules the total amount of energy given to alpha particles that are emitted between time t is equal to 0.3 seconds and time t is equal to 0.90 seconds. So the first thing we need to understand, it is given to us that number of alpha particles emitted, we can say number of alpha particles emitted. Number of alpha particles emitted is equal to number of decays. Number of decays. Or simply we can say is equal to number of polonium nuclei decayed. Number of polonium nuclei decayed. So this is very important point. So number of alpha particles emitted, we can simply calculate. That is equal to number of polonium nuclei decayed. At time t is equal to 0.3 seconds, we have this much number of polonium nuclei. And at time t is equal to 0.9 seconds, we have this many number of polonium nuclei. So we can calculate number of alpha particles emitted. So simply we have 16 times 10 to 12 minus we have 7.2 times 10 to 12. So here we have number of alpha particles emitted. Now we need to find out total energy given to alpha particles. Total energy given to alpha particles. So we can write on here total energy given to alpha particles, and that is equal to number of alpha particles times energy released in one decay or energy given to alpha particle in one decay. So simply we can write on here, this is 16 times 10 to 12 minus we have 7.2 times 10 to 12. We have to multiply this one with energy given to alpha particle in one decay. That is equal to 6900 kilo electron volt. Now we have to convert 1 kilo electron volt into joules, and 1 kilo electron volt is simply equal to 1.6 times 10 to negative 19. This is kilo, so we have to multiply this one with 3. So simply we can say this will be equal to 1.6 times 10 to negative 16. So we have to multiply here with 1.6 times 10 to negative 16. So if we multiply this, we can find out our final answer. So the final answer in this case will be equal to 9.7 joules, and this is the energy given to alpha particles in this number of decays. So this is our final answer. So this is very important point you need to understand. So in this case we can say 1 is equal to 1.6 times 10 to negative 16 joules over kilo electron volts. So this factor you have to understand. For the second part, we need to suggest why the total amount of energy released by the decay process between t is equal to 0.3 second and t is equal to 0.9 second is greater than the answer in C1. So it simply means that we can write down here total amount of energy released, E total released. This one is greater than energy of alpha particles. So we need to explain where extra energy has gone. So we can write down here, first of all, extra energy. Extra energy in fact become kinetic energy of Pb nucleus plus gamma photons. So we can say gamma radiations, or you can say gamma photons, gamma radiations. So in any decay, gamma radiations are always emitted. So the extra energy has gone to kinetic energy of lead nucleus and in form of gamma radiations. Now let's try to understand how it becomes kinetic energy of Pb. Polonium nucleus, initially this is at rest. So this nucleus is at rest. So I will redraw here polonium. Polonium initially initially is at rest. So U is 0. So the momentum of this one, Pi, is also 0. So momentum has to be conserved in any decay. So after this decay, we have two particles. One is nucleus of Pb and one we have alpha particle. So if alpha particle go, for example, if alpha particle go to the right, Pb has to go to the left to conserve momentum. So Pb has kinetic energy. So all the energy is not the kinetic energy of alpha particle. Energy released in this decay become kinetic energy of alpha particle. It also become kinetic energy of Pb, and also it is energy of gamma radiations. So final momentum has to be conserved. So P final has to be equal to P initial. So that's the reason these particles have to go in opposite directions. In this case, most of the energy will go to alpha particle because it has very small mass, and less kinetic energy will go to lead because it has higher mass. But momentum of alpha and momentum of Pb has to be the same and in opposite directions. So this is the reason. You can write any one of them. So let me show you how you can write down the answer. You can say it becomes kinetic energy of Pb, or you can say it is released in form of gamma radiations, or you can say in form of gamma photons. Any one point you can write down. So this is how you can write down your answer. This question has 1 mark. So if you write down lead nuclei have kinetic energy, you will get 1 mark. Or if you write down gamma photons are also emitted, so the extra energy is energy of gamma photons, you will still get 1 mark. So this is how we can answer this type of problem.